Okay, I think we'll get started. So we're coming into this idea of chemical equilibrium, and last time we set up the equilibrium constant and the reaction quotient. Today we're going to talk about criteria for equilibrium, and we're going to see two of those, one related to the chemical potential and one related to the Gibbs free energy. So let's get into that. So let's just recall some things we've learned about now. We've learned about these auxiliary functions, and in particular, the Gibbs free energy function. And this is defined this way relative to the total internal energy. So these are these Legendre transformations that we did. And if we want to write it in terms of enthalpy, then we notice that this bit is H, and so we have H minus Ts. We've talked about generalized force, generalized displacement, and so work can be written as the sum of all the different contributions of generalized force times generalized displacement. So this really fancy A, big A, capital A, D, little fancy a, representing the different types of generalized force, generalized displacement. And then, like we just mentioned, we have talked about Q and K, and we have the mantra products over reactants. We know what that really means. It means products raised to their stoichiometric factors divided by reactants raised to their stoichiometric factors. So hopefully you've had a chance to practice this and you've remembered some of these things from earlier. All right, so let's just apply the first law of thermodynamics to the very simple reaction A goes to B on the lab bench. So a very common situation is doing chemistry in the laboratory, and that's what we're focusing on. This would be very similar to doing chemistry in the body, so biochemistry. There are certainly other places we do chemistry, but in the lab, that's a very important case. In the body, that's a very important case. And in the lab, at least during the course of an experiment, the temperature and the pressure are held constant. So those are good independent variables that we just keep constant. In the body is very good at keeping constant temperature and constant pressure. And so it's good to have temperature and pressure. We'll get to that. So in the lab conditions, what we really mean by this lab bench conditions is the reactions done at constant temperature and constant pressure. Now, I think there's something that can be a little bit confusing here. Let's say we have a reaction that heats up. And we say, well, that's not a constant temperature. We have to remember what we're doing is we're thinking about the state of the reactants at a given temperature, pressure, concentration, and so on. And then the state of the products at a given temperature, pressure, and so on. And when we talk about when we talk about the reaction, we talk about at, say, 298 or whatever temperature we want, and then the reactants at that same temperature. So maybe it heats up, but then that heat is let to dissipate, and eventually the system comes to equilibrium, thermal equilibrium, with the room around it. So that can be a little confusing. You think, oh, this reaction heated up so the temperature's changed. Well, it momentarily changed, but in sort of infinite time, it has come now to the same equilibrium with the room as it started. And same with pressure. So lab bench, constant temperature, constant pressure. Now, let's get into the first law here. So first law is work, right? Or is heat plus work. Right? So a little change, infinitesimal change in that total internal energy is due to a little bit of heat exchange or a little bit of work exchange with the environment. Let's use our generalized force, generalized displacement. So we can talk about pressure volume work, and then we have the chemical potential work as well. So the chemical work. So the chemical potential is the potential to change the amount of material. So for the case of A, we have a chemical potential associated with species A, and we have a chemical potential associated with species B, and there's a certain amount of energy to change the amount of A or B in the sample. Now, we're not saying that this is open and A and B can leave the sample. So we've got a otherwise closed system. So the only way for these things to change is through the chemistry. It's not through evaporation or some other means. Okay, well, let's do something we can do. Let's say, well, let's limit this to just a reversible change. And in a reversible change, according to the second law, or the thermodynamic definition of entropy, dq is TdS, so we can make that replacement here. And then P external is equal to P, so any kind of volume change in this associated with this reaction is happening such that we're in equilibrium with the external pressure at every step of the way. And so P external equals P, and so we have this. Now we say, okay, well, now we're under reversible conditions, but we appeal to the fact that these are all now state functions, and so they're path independent, meaning we got to this little change by choosing a path, a reversible path, but because everything there doesn't care about the path, this is still a general statement about this equation, this reaction happening here on the lab bench. Now, if we look at the change in U, what's causing that change? A change in S, change in V. So the natural variables S and V. But now we have the possibility to change the amount of material that can also change U. And so we have actually 4 natural variables: S, V, N, A, and NB. Now, NA and NB we're very interested in if we're keeping an eye on the chemistry, if we want to learn about the chemistry. S and V we're not very interested in. And they're hard to control. Volume not so much, but entropy, I mean, how are we going to control the entropy in our reaction? So this is where the auxiliary functions really start to pay off. So we will switch now to describe the reaction happening at the lab bench with the Gibbs free energy. So let's write that. The Gibbs free energy is a Legendre transformation that will get rid of these, swap these out. So these flip-flop. So we get a minus S dt, so natural variable temperature, natural variable pressure. And what did we say about the conditions of the body or the lab bench? Constant temperature, constant pressure. And so that's why this is going to be so valuable to us. The stuff that isn't focused on the chemistry is just gone. And then what's left? DNA, DNB, which is exactly what we're interested in. That's the chemistry. So 4 situations where we can control the pressure and temperature very easily, body, lab bench, many other areas, then Gibbs free energy is the free energy to use. So we're down to this now. Right? We've isolated in on the essential chemistry. So now we should do some chemistry. So we said we're in a closed, otherwise closed system, so the only thing these can do is go back and forth. If A changes, B changes. There's no way to avoid it. And in fact, if A changes by 1 molecule, B changes by 1 molecule, but in the reverse direction. So 1 molecule of A has turned into 1 molecule of B. Or on a molar level, 1 mole of A has turned into a mole of B. And so a change in B is equal but opposite a change in A. So we can think of an infinitesimally small change. So just think of 1 molecule. Compared to a molecule is essentially an infinitesimally small change. And we get then this relationship. So let's just, we don't need 2 separate changes. They're linked together, so we can describe it as one. We'll just call that dn. So dn will be equal to nb, and then so wherever we see a dna, we need to put a minus dn. So that's going to go right here. So this term, this minus comes in here. This goes as is, and then we get this expression. All right, so this is telling us how the little change in Gibbs free energy occurs with a little change in amount of material at the lab bench. So now we have to appeal to what chemical potential is. So chemical potential physically is the driving force, the generalized force to change the amount of material. And there's a competition here. There's a chemical potential of B, and a chemical potential of A. If B is greater than A, then it wins, and it pushes B out of solution. The only way to do that, because it can't escape the system because we're otherwise closed, is to create A. And so if the chemical potential of B is stronger or greater, more positive, we'll say more positive than A, then B will go to A. Under those conditions, this is bigger than this. dN, we're taking dN to be, we take dN to be positive, and so dN, so if this is bigger, then our delta G is greater than 0. Now, the converse, if A is stronger, then A will force more B, and the reaction will go this way. If we look at this, then this is negative, so delta G is negative. Okay. Then finally, we have a condition of equilibrium, or a criteria for equilibrium, and we have two here. So we have two equally valid and equally important criteria for equilibrium. At equilibrium, the chemical potentials are equal, which makes good physical sense. The driving force to change A is equal to the driving force to change B, and so we've come to this chemical equilibrium. We don't see any net change. And then delta G is 0. So delta G equaling 0 is an important criterion for equilibrium that we'll see over and over through the whole curriculum, actually. All right, well, this was a pretty simple reaction. This was just A goes to B. There is some subtlety here, so let's walk through a couple of examples of a little more complicated stoichiometry, and then we'll get all the way to the final, just a completely general reaction here. So what if we go from, if A goes to, from A to 2B? Well, what has to change, everything stays the same. We can work with delta G. What has to change is this chemistry relationship between the DNs. So if one molecule of A changes, 2 molecules of A are produced. So you just read that from the chemical reaction. So we're going to let 2dN be equal but opposite dNA, and we'll call that 2dN. So the dN is going to be the same value as dNA except opposite sign. And so when we do that, then when we plug this in, we get our negative, and then 2, that 2 comes along, and that 2 is the very same 2 that's sitting up here in the stoichiometry. And so we get this. And again, our criteria for equilibrium is going to be when delta G is 0, or when these are equal. So if those are not equal, we will change the amount of material. But notice we're leveraged by this stoichiometric factor. So we have the same relationship, but we include the stoichiometric factor. And we read it straight from the reaction. So it's as simple as taking the reaction and then just writing mu A equals, instead of the arrow, to mu B. Okay. All right, what if we have multiple components? So let's look at this reaction. Then to make a change in C, we have to remove 1 molecule of A and 1 molecule of B. And so we're linked in this way. dNC is minus dNB minus dNA, which is minus dN. And so we can plug that in for delta G. And our criteria for equilibrium then, we need that to be 0. And so again, we have reactants. We just take the reaction, read as is with the stoichiometry, change the arrow to an equal, and change the species to the chemical potential. And then that follows through for any reaction. So you can kind of see how we would just do this same thing for an arbitrary stoichiometry, and we get this criteria for equilibrium. So there's this, and dG equals 0. So those are our equilibrium conditions. Now when it comes to a reaction, we write delta reaction G. Okay, if that is 0, then we're at equilibrium. That's our condition for equilibrium for a full reaction. All right, so we'll start talking about this. We're going to get what's called the delta G equation, so that's coming up, and that will be the central equation in equilibrium chemistry. Not a lot of homework for this right now. Just keep practicing the K and the Q stuff from last time. Think about this. Really try to go through, take a blank sheet of paper, see if you can do this. It's very easy to get yourself turned around and actually invert the stoichiometry. So you can try it, and then just remember, you know the answer. The answer is going to be just read the reaction as is. See if you can get from here to here without fudging any numbers or going, oh yeah, just remembering this. Play dumb and just start here, try to get to here, and then you can always check your answer. It should match your reaction for whatever reaction you write. All right, so we're right now in the heart of this chemical equilibrium.